So we're going to transition into talking about the cross product. And the cross product is just another way, like the dot product, to multiply two vectors, but there's going to be a big difference here. So the cross product sometimes you'll hear also vector product. The cross product of two vectors. And I'm going to go ahead and sort of explicitly write their components out because it's going to depend on what those components are, the cross product. So it's denoted U cross V. Okay. And so notice here that I've chosen U and V to have three components, and that's because fundamentally the cross product is a three-dimensional operation. So really when you take a cross product, you want to be thinking about vectors in three-dimensional space. And so what is it? It's denoted like this, U cross V. And this is what it is. So it ends up being a vector, and I'm just going to write this down, and then we can think about what's going on. So the first time you see this, it might look a little bit crazy. But there is going to be a nice way to actually sort of remember what it is. Just want to make sure that I get it right, writing it down the first time. Okay. So there it is. So it's a vector. Here's the x component, here's the y component, here's the z component in terms of the x, y, and z components of u and v. And you look at this and you say, how in the world am I ever going to remember this or even, have a feel of how to use this? Well, there's a much better way to remember what the cross product is if you actually remember how to take the determinant of a 3x3 matrix. So you can also write U cross V is equal to, and I'm going to sort of write this in a formal way. So I'm going to write this unit vector in the x direction, unit vector in the y direction, unit vector in the z direction, ijk, and then I'm going to put in the second line of the matrix, ux, uy, uz, vx, uy, vz. Okay, so it's just equal to this determinant. Now, if you remember how to take the determinant, you're just going to take this I and then block out the row and the column that it's in, and then do this uy, uz, uy, vz, and then you have a minus just for taking the determinant. You have the j component, so you block out the row and the column, and then you have the determinant of the smaller matrix, ux, uz, vx, vz, and then plus k component, which is, and then the component is just the determinant of, okay, I block out the row and the column that k is in, ux, uy, vx, uy. Okay, and if you compute this out, you're going to get exactly this, this, and this. So here's the x, y, and z component, but just written in maybe an easier to remember way, if you can just set up this determinant. Okay, so I made the point that the dot product was a scalar, but the cross product is actually a vector. And so it can actually be verified that this vector u cross v is always orthogonal to u and v. And so if you think about this in terms of a picture, if here we have u, and now we really got to think in terms of 3 dimensions here. So we have v right here, then you can show that the cross product is actually going to point down this way. And now again, we want to think sort of 3-dimensionally here. And those are actually right angles, so this is the vector u cross v. So it's orthogonal or perpendicular to both u and v in 3-dimensional space. And so you kind of should notice that you have a choice here. So I could have also drawn u cross v up here. How did I know that it pointed down perpendicular to u and v and not up? Well, the distinction comes from what's called the right hand rule. And what does that say? Well, it says that if I'm looking for u cross v, I start in u and I point my fingers on my right hand towards u, and then I curl in towards v, and the direction my thumb is pointing is the direction of u cross v. So I point to u and I curl to v, and notice that my thumb is pointing down this way. But if u were this way and v was out like this, then I would point in the direction of u and then curl to v, and I would notice that actually u cross v would be pointing up. Of course, perpendicular to both of these vectors. Like that. So this is an important thing to remember, and this is sort of conventional, and it's just the fact that we use kind of a right-handed coordinate system, that we have this right-hand rule. But again, the key thing to take away is that u cross v is a vector, and that it is actually orthogonal to both u and v, and just kind of depending on how u and v are oriented with relationship to each other is whether it goes up perpendicular to both or down perpendicular to both. So we reviewed some of the properties of the dot product. The cross product has some properties we can review as well, but they turn out to be maybe a little bit more complicated than the dot product. I mean, sort of fundamentally, the cross product is a more complicated thing than the dot product. So first of all, we don't have, so remember the dot product was commutative. It didn't matter which vector we put first, but the cross product is actually what's called anti-commutative. And what that means is that if I take u cross v, that's not going to be the same thing as v cross u. It's actually going to be equal to minus v cross u. So it's going to be a vector pointing in the opposite direction. And we've kind of already seen that. So if I switch the order, I pick up a negative sign there. We can also think about what happens if I multiply by one of the vectors by a scalar. So if I take a scalar times u and then cross with a vector v, well, this actually is just the constant times the vector u cross v. The one thing that the cross product does behave well with is vector addition. And this is very similar to what we saw with the dot product, kind of this distributive property. If I take u and I cross with the sum of two vectors, you do sort of do exactly what you would think, and it's u cross v plus u cross w. And of course, all of these would have to be verified just from the definition of the cross product, but I mean, I'm not saying it's difficult to do. It's just maybe a little tedious, but I mean, these are important things to keep in the back of your mind, or at least just remember that, you know, properties like this exist if you ever need to look them up. So another interesting thing is how the cross product behaves with the dot product. So what if I take a vector and I take the dot product with the cross product of two vectors? Then what we get is we can actually switch over and first just take the cross product of u and v and then dot with w. The last thing to think about is sort of an associativity relation. So what if I take u and then cross with v cross w? Now this is where things get weird, because you probably, if you're familiar with the associative property, you would think, okay, I can probably just move the parentheses and do u cross v and then cross with w. But that's actually not the case. What you actually get here is you get u dot with w in the direction of v minus u dot v in the direction of w. So you can verify that this is not the same thing as u cross v in parentheses cross w. Okay, so now that we've talked a little bit about the cross product, we've said what it is and some of the basic properties that it satisfies, you're probably wondering what in the world is the purpose of the cross product. But what we're going to see is that the cross product is very important for us, especially later on when we talk about surface integrals and surface area of surfaces, stuff like that. And so recall that the dot product had the interpretation that it was the angle between two vectors. So what about the cross product? Well, if I take u cross v and I look at the length of u cross v, well, this is actually going to give me something. This is the area of the parallelogram. And I'm going to use this word and I'll kind of say what I mean, spanned by u and v. Okay, so what do I mean by that? Well, if I have u here, and I have v here, and so we'll see that this is just sort of lying in a plane. These two vectors, even if they're in space, they're going to be lying in the same plane. Well, I can translate v up here It's kind of what we saw when we added the two vectors together. And I can translate u over here and sort of form this parallelogram spanned by u and v, like that. And so the area of this parallelogram is going to equal u cross v. But there's also another way we can think about the area. And this is sort of looking back at our projection. So if I draw this vector here, it's sort of the orthogonal projection, and I look at the angle between u and v, then what I see is actually the area of this parallelogram is just the length of v times the height of the parallelogram, it's just base times height. And so actually the area is also, the height is just going to be the length of u times sine theta. So the area is just here. And so the way you show that the area is equal to the length of the cross product is you show that the cross product, the magnitude of the cross product is actually equal to this expression here. So another thing about the dot product is recall that two vectors u and v are orthogonal, and you can just think orthogonal is just a fancy word that means perpendicular, if their dot product equals 0. So the cross product is actually going to give us a way to determine if two vectors are parallel, or pointing in the same direction. I guess I should say in the same direction or in opposite directions, right? So they're on the same line. So we say u and v are parallel if, well, guess. If this length of the cross product is 0. Or in other words, the area spanned by u and v are 0. And you can see if u and v are in the same direction, they're going to create a parallelogram that's flat, that has 0 area. So these are two very useful tests to determine whether two vectors are orthogonal, or in other words, perpendicular, or if they're parallel. Okay, so we're going to do one more little piece of geometry, and we're going to define what's called the scalar triple product. And now we really need 3 vectors here because it's a triple product of u, v, and w. And it's just going to be u dot v cross w. And again, I mean, this is just something that you can just think is made up. I mean, you just take 3 vectors and then you just have a way to assign a number to them. You just take the cross product of 2 of them and then dot with the third. So the magnitude I'm going to tell you why you would even think to define something like this. Well, the magnitude of this triple product, and notice that This is going to give me a scalar, but it could be negative, so I just need to take the absolute value and make sure it's positive, is the volume of, and here comes a word, parallel hypid spanned by these three vectors, u, v, and w. So again, the best way to see this is to draw a picture. So let's say I have, here's v there, here's w down here. Let's say this is u right here. Well, what I can do is I can translate v, translate w, there's w again, there's v again, and then I can put u again over here. U, again, over here, u, and then I can put all the other vectors here. So I'm just sort of translating these vectors around. This would be w, this would be w, this would be v, this would be v. I understand that this picture maybe is becoming less clear the more I draw on it. But remember that v cross w, the magnitude, was the area of this parallelogram down here. And the volume of this parallelepiped will just be its height. So I just need to project u onto sort of this height vector. And this vector actually is u cross v. This is actually v cross w. So I just want to project u onto v cross w. So I can think about that in terms of an angle. And I work this out, and I take the volume, and I see that the volume of this parallelepiped is exactly this triple product. So that's sort of the idea. And the details are just something you can just sit down and work out. But it's just a useful fact to know that the magnitude of this triple product gives you sort of this volume of this box-like object called a parallelepiped. Okay, so we want to find the cross product of these two vectors, and I'm going to use this determinant mnemonic. So we have I component, j component, and the k component, and then I'll just write in 1, 2, 4. Notice this says u cross v, so I put u first, and then v is 1, 1, 1. So this is just going to be an I component, which is 2, 4, 1, 1. So I just remove the row in the column that I is in, and then minus, that's built into the determinant, j, and then we have 1, 4, 1, 1, and then plus the k component, which is, just remove that, so 1, 2, 1, 1. And so we can just write this as a vector now. So the x component is 2 minus 4, so minus 2. And then minus 1 minus 4, so minus minus 3 goes positive 3. And then 1 minus 2 will give us minus 1. Okay, there's the cross product. Not so bad. And then for b, we'll do the same thing. We'll have I component, j component, k component. Then we'll write in -1, 1, 1. Of course, the order matters because I want U cross B. 2, -2, -4. Okay, and this equals, okay, the I component is 1, 1, 2, -4, minus the j component, -1, 2, 1, -4, plus the k component, or the z component, is -1, 1, 2, -2. So this is going to be -4 minus -2, so -2 will be the x component. The j component will be 4 minus 2, which is 2, but it's minus, so -2. And then the k component, we have 2 minus 2, so 0. There it is. All right, so we want to find the area of the parallelogram formed by these two vectors. And we know that the area is going to be the length or magnitude of the cross product. And now, you may be wondering, okay, so don't we normally have 3 components when we take the cross product of 2 vectors? Well, the answer is yes. And so really, what we should think about here is, okay, these are lying in the xy plane, so just say, okay, well, the z component is 0. Because the cross product is actually going to point out of the page. It's not going to be in the page. It's going to be perpendicular to the page because both of these vectors are lying in that page or plane. And so what we have here is the absolute value of the determinant so we have I, j, k, 1, 0, 0, 1, 1, 0. So the determinant, but we need to take the absolute value. Okay, or the length is what I mean. And so we want the length of the vector. Okay, so the x component here is going to be 0 minus 0, so just 0. The y component is just going to be 0 minus 0, so again 0. And then the k component is going to be 1 minus 0, so 1. Okay, so we just want the length of this vector, but this is a unit vector. It has length 1. So the area of this parallelogram is 1 unit. Okay, so the volume of this parallelepiped formed by these vectors is just going to be the magnitude of the triple product. And actually the cool thing about the triple product is it's not going to matter if you think back to those properties of the cross product. Maybe you didn't really think much of them, but actually within there shows us that if I take any triple product, they're all going to have the same magnitude, right? They might just differ by a sign if I switch two of them or something like that. So I'll just do 1, 1, 1 dot, and then the cross product 1, 0, 1 cross 0, 1, 1. So the volume is just going to be the absolute value of this. Okay, so what's the cross product? Let's do the cross product first. It's in parentheses here, and then we'll take the dot product. So 1, 1, 1. Let's just see if we can do this. Okay, so I, J, K, 1, 0, 1, 0, 1, 1. Okay, which is 1, 1, dot. Okay, the I component is going to be, let's see, 0, minus 1, so minus 1. And then the J component is going to be, looks like 1 minus 0, but it's going to be negative. And then the K component is going to be 1 minus 0. So again, just 1. Okay, and then let's do this dot product. So minus 1 plus minus 1 plus 1 is just going to give me minus 1. But then the absolute value of 1 is negative 1 is just 1. So the volume of this parallelepiped is just 1. Okay, so I'm applying this force to this door at this angle with a magnitude of 20 newtons. And here, it's not labeled, but this is our hinge right here. Okay, so I'm pushing in this way. It's making an angle of 45 degrees. Okay, and so, well, what is torque? Torque is a vector, which is the force applied. Let's see. Actually, it's going to be R, where R is the displacement vector from the hinge cross with the force vector. So here, it's like our R vector right there. So the displacement from the hinge where we're applying the force, and of course this is our force vector, 20 newtons like that. Okay, cool. And so the torque in this situation, so what is R? R, it says a distance of 1 meters, and that's to the left of the hinge, so we'll put negative 1, 0. And actually we'll again put in a 0. We're working in a plane here, but we'll put 0 for the z coordinate. And then the force vector is, so it's negative 20 cosine 45. So that's this component, the horizontal component this way. So it's the adjacent side right here. And then the y component is positive 20 sine 45. And then of course the z component is 0 because we're working in a plane here. But the torque will point out of the page. Okay, so what is the torque? Here we go. I, J, K, we have negative 1, 0, 0, and then we have, so let's just go ahead and figure out what this is. So cosine of 45 is root 2 over 2. Sine 45 is root 2 over 2. So this is going to be negative 10 root 2, and this is going to be 10 root 2. Okay, so negative 10 root 2, 10 root 2, 0. Okay, and this is going to be, well, the I component is going to be 0. We already knew that. It's going to point out of the page. So as is the J component. Okay, And then the z component, which we're thinking about being in and out of the page, is going to be negative 10 root 2. Okay, so there's the torque vector. But we want the magnitude of the torque vector. Well, that's just going to be, well, there's only one component here, so it's just 10 square root of 2. And then the units here are going to be Newton meters, because the force is in newtons, and then the displacement vector is in meters.